Yeah.
So I left off last time, and I didn't do. I was going to do a Globus demonstration for data transfer. Is that something you guys are interested in?
That was transferring like data from like my machine to.
From your machine to SCF, from SCF to Savio, from Savio,
That
wherever.
sounds useful.
Okay.
Well, isn't this just SFTP?
Huh?
CP.
Save file
So yeah,
transfer.
you can use SFTP and SCP in those things, but Globus. The nice thing about there are a couple nice things about Globus. One of them is that it is really fast. So it's much faster than often much faster than using SCP or those sorts of things. And also it sort of does fault correction, and so it'll like you can set it running for like if you're going to transfer like 50 gigabytes, you can set the transfer running, and then it will handle if it gets disconnected, it'll reconnect and do things like that, so you don't have to like manually watch over it. So the way that you basically do it is you get an account with this globus.org, and then you have to log in, and you should be able to log in with your Berkeley credentials, and it probably is already logged in for me. I don't know why it's so slow.
Can you set it up to basically always synchronize between two machines without me having to do anything?
I don't think it's designed so much for that. Yeah. So then you can select, where's Berkeley here? Okay, so then you can authenticate with your Berkeley credentials. And then once it's going, it basically gives you like a graphical interface like session. And so it has this notion of endpoints. So an endpoint could be your laptop, an endpoint could be the SCF, an endpoint could be Savio, an endpoint could be some other party that provides an endpoint. And so basically, if you want to transfer from your laptop, you have to make sure you have an account, and you have to make sure you have this Globus application installed. So that's what this little tab is up here. It shows that I've got it shows I have this Globus Connect Personal installed, and that it's running. And then, Jesus, that's really slow. And so then the sorts of things you can do are you can say, okay, I want to, you can click on UC Berkeley statistics, and then usually it will prompt you for your password, but I think I entered my password earlier today, so it didn't prompt me for it here. And then I could, and as the other endpoint, I could, for example, go to, I've set up my laptop as one of these endpoints, and there's a whole set of instructions for doing that. But once you've done that, you can go to this, and I called it Work Laptop, and so then it will show a view of my, home directory on my laptop. And at this point, I can basically just click and then click on one or more directories, and then hit either arrow depending on which direction I'm going.
How do you set up the endpoint to be the statistical again?
Oh, so you just basically click on endpoint. It's like the usual story with when things are slow, you have overreact. If it wasn't already among them recently used, you could use, I think, just like typing UC Berkeley statistics would work. Yeah, so just need to type in enough keywords that it recognizes it. So it's a nice way to transfer a lot of data between different locations. Obviously, you're going to be limited by the bandwidth if you're at home, by the bandwidth that your internet provider is giving. So this is particularly useful if you're like transferring someplace that provides a huge amount of data and you want to transfer it to the SCF, or you want to transfer it to Savio and transfer gigabytes or even terabytes of data. And you can control at the bottom down here, you can control this business of like, well, am I just syncing it, or am I transferring everything that I indicated, fresh? And then things like preserving times and things like that. So once you do a transfer, it will basically, so I could like, let me just find a file to transfer here. So if I now click and say I want to transfer that file to my work laptop, it'll say I submitted the request, and then it'll do it sort of asynchronously, so it'll do it in the background. And if you go to activity, it'll basically show you the transfers that you've done recently. So in this case, this is the transfer that I just did, which was a small file, so it was basically instantaneous.
And then I could close the window and go for workout or whatever, and it's going to do it.
Yeah. Yeah.
Okay.
Yeah.
That's pretty
I can't log in, so I could
Really?
like
That's fine for me.
linking arrow.
Oh no, you don't want to link. So when you logged in,
No,
and then
I
it came to
can't.
another thing,
I
and
can't
you clicked.
I can't
No,
like.
go back and log in again. But then when it goes to link or don't
Is
do
this
this,
application
click on don't do it.
have for the Unix system or?
Yeah, it's Mac Linux Windows.
Yeah, it provides clients for all of them. If you are, if you're not, if your laptop is not involved in the transfer, then you can do it all through the web,
Oh,
which is what I'm doing. Which is, this is just a web browser here that I'm doing the transfer through. It just happened that I needed this little icon up here. I needed the client running on my laptop because my laptop is serving as one of the endpoints for this particular transfer. So.
either way to do command line.
Yeah, Globus has a command line option, which I've never gotten far enough into it to figure that out. But there is some information on the web for doing that. Or if you end up trying it out and want more information, I can help you look into it more. It's something I've sort of been meaning to do, but never have gotten around to. Okay, any other questions about that? Okay.
Is this what you use to transfer?
If I'm transferring like multiple gigabytes, then I will I don't usually transfer that many gigabytes all that often, but if I'm transferring multiple gigabytes, then I will use this.
Faster.
Yeah, it's faster and because I don't need to worry about what if it gets interrupted and whatnot. So when I was setting up a demo for the Stat 243 class tomorrow, where I was transferring like, I thought that was mine at first, where I was transferring I think 20 or 30 gigabytes from either the SCF or Savio to a National Science Foundation computer called Bridges, which is at one of the supercomputing centers, and so I said I did it using Savio. I mean using Globus, yeah.
Wait, you don't have to worry about it getting interrupted?
Nope, it does it all automatically. Because you enter your authentication for both of the locations, the to and the from location, and so then it can then basically sort of log in as you and figure out where it got interrupted and then continue the transfer.
So,
Yeah. So it's pretty cool and pretty useful.
So is this something that Berkeley subscribes to, or?
Yeah, it's sort of a weird operation. I think it's a nonprofit, but it's actually fairly expensive for institutions to access it. And so Berkeley has some sort of agreement, and there are like different tiers of agreements. So there are some things you can't get through Berkeley because we haven't paid enough money to them to get them. So. Okay. So the materials here are on the same repository as from last week. So if you did if you re-pulled from Git, you should be able to refresh the stuff that I added over the last few days. And then, as I mentioned, I guess I didn't say this explicitly last week, but all of the material here is basically a subset of the tutorials I have online on the SCF website. And so there are links here to, I have one tutorial on working on one machine, which I'm calling shared memory, and another tutorial for working on multiple machines or nodes, which I'm calling distributed memory processing. Okay, so I thought what I'd do based on, I don't know how many of you were amongst the ones who filled out the survey, where I got like 10 or 12 responses, and there are a small subset of you here. So I sort of tailored it for that response, for those responses. I don't know how well that maps onto this. But I'll give an overview of sort of some of the different ways people do parallelization. I'll talk about some of the sort of high-level strategies for splitting up computations. And then I'll go through a few examples of doing things on one machine or doing things on multiple machines in Python and in R. And then I'll probably say a little bit about random number generation in parallel, and then time permitting a little bit about using MPI. Actually, were any of you the ones who were interested in MPI in the survey?
What is it?
I can't remember.
Huh?
I can't remember. Depends on how you word it.
Okay.
What is MPI?
What is MPI? So MPI is the protocol by which a lot of parallel programming gets coded for communicating across machines. So if I have time, I'll say a little bit about that.
One question about Globus.
Mm-hmm.
Are the destinations physical computers, or can you do Google Drive and Dropbox?
Yeah, so that's a great question. So they are, yeah, I don't think, I mean, what it means to be a physical computer is a little bit nebulous anyway, so I don't think that they're restricted in any particular way like that. I think Berkeley was actually trying to coordinate with Globus to set it up so that Google Drive or Berkeley Drive could be an endpoint, but I don't think that's in place yet. And at some point we were also trying to figure out if there was a way to do that with Box too, but that's definitely not in place. So those things are still sort of on the horizon. But if those were available, that would be great because of the free storage that Box and Drive give for Berkeley people.
So where do you store your data?
I mainly store stuff on the SCF just because that's where I do most of my computing. Yeah. Okay, so we basically said this last week, and you guys I think were all here last week. So we've got multiple cores on a given node or machine. We've got multiple machines making up a Linux cluster. We're going to have generally run one process per core amongst the collective cores that we have on all of our machines. And those are sort of the key things to keep in mind. Okay, so some of the ways that people will do parallel processing are, sorry. Is they will on one machine use threaded code, and so you can write C or C++ code that involves something called OpenMP, and that basically allows you to take a given sequence of operations in your C or C++ code, and then at the point where you get to like having a for loop that you could parallelize, it sort of splits into different what are called threads, and those different threads would operate on different cores of your machine. So if you want to go the route of coding your own, you can do that. These different the linear algebra packages that we have R and Python linked to, like OpenBLAS and MKL, these are all threaded linear algebra packages. So they're basically, I think they probably even are using OpenMP explicitly behind the scenes. So when you then do like a big matrix multiplication, it's basically within the 3 for loops that are involved in doing matrix multiplication, it's splitting up some of those for loops across the multiple cores. And so whenever you did if you have code that's running that's threaded like this, if you ran top to look at your different processes, so have you guys all familiar with top? No. Okay. So if you're on this is R1, which is one of the SCF Linux machines. If you run top, you'll basically see all of the different processes that are running. In this case, there's nothing running. There are a couple things running. So you can see a few people are doing a sort of haphazard collection of different things. And you'll see in this column, you'll see the CPU usage. And so in this case, Dave Graham Squire is running Chrome, and he's using about 40% of CPU. If there were a process that were running that was threaded, you would often see more than 100% of the CPU, and that means that one process is using more than one core, so you can go up to more than 100%.
So what is the difference between several processes, each using like 100%? Compared with one threaded process that is used.
Yeah, I mean, for our purposes, maybe a computer scientist would want to, go off on the tangent and say a lot about it. But for our purposes, it's not particularly important. Like you're basically using multiple cores, and regardless of how the operating system sees it, you're using multiple cores. But it is handy just to at least know that if you see more than 100%, that means it's threaded. If you don't, then it means that your one process has started up multiple independent processes. Okay, so basically, so then the other kind of functionality which I'll focus on today is basically when you have a single R or Python process running and you tell it to parallelize some code, and basically it starts up some independent worker processes, and then it manages sending the additional computations to the workers and collecting the results back. So if you do that, what you'll see in top is you'll see multiple R processes or multiple Python processes. Ideally, each one of them would be running at 100% so that you're fully utilizing the cores that you have access to. Okay, so then distributed memory gets more complicated because you basically have to manage the process of starting up workers on other nodes. So all your nodes need to be communicating appropriately with each other, which can cause headaches to set up. Yeah?
So how do you get over 100% if different processes use different cores?
You don't unless your code is threaded. In general, you won't see more than 100% unless you have a single process that is threaded that ends up using multiple
cores. So when you say different processes, you mean each one is just single threaded?
Yeah.
Okay.
Yeah, that's in general what I'll mean. You could have, and there would be ways to do this even in R and Python, where you have you've parallelized across different processes, and then each process is itself threaded. For example, using linear algebra, and then you'd have multiple processes, each of them over 100%. Yeah. So if you're doing things across multiple machines, then the sort of complicated things that you can do are to use MPI, and that's what people traditionally call high-performance computing. Like if you think about the supercomputers up the hill at NERSC or places like that. And basically what MPI involves doing is that you have multiple processes running. So you might have process 1, process 2, process 3, process 4. And what your code will do is your code will basically say, hey, process 1, send this bit of data to process 2. And then you'll have another line of code that says, hey, process 2, send some data to process 3. And you'll basically write all of that code manually to say, what do I need to send to which of the processes, and then what are they going to do with the data, and then when they finish with it, maybe they're going to send the result to a different process. So you have to sort of manage all of that communication. So it's quite tedious. People still do it, but if you can avoid doing it, then you probably want to avoid doing it. And most of the things that we do in statistics are fairly easily parallelized, and you can get a lot of bang for the buck just out of parallelizing your bootstrapping, parallelizing gradient computations, parallelizing cross-validation, those sorts of things.
So just for my understanding, when I use an R for each, I would do multiple threading, but I wouldn't start multiple processes.
No, that would be multiple processes.
It would be multiple processes, and when would it be multiple threading?
Yeah, so it would be multi-threaded if you were using one of the threaded linear algebra packages behind the scenes, and it would be multi-threaded if you wrote your own OpenMP code. And MATLAB also uses threading for a variety of different operations, so you might see that happening in MATLAB as well if you were running MATLAB.
Okay, so I would, if I then type in top, I would see multiple processes.
Right. If you've started multiple processes, you'll see multiple lines. If you're using threading, you would only see one line, but more than 100%. But like I sort of said before, it's not really, maybe not all that important to distinguish between them for our purposes of doing things. But it may be handy just to recognize that. So you could write C or C++ code where you use MPI syntax to do that kind of communication. MPI, you can also with MPI just do simpler things like MapReduce kinds of things. So you could basically broadcast out a whole bunch of data for different workers and then execute the same code on all those workers and then collect the results back. That you can do those sorts of things. And then you can run MPI through R, through the RMPI package, and through Python through the MPI for Py package if you wanted to do it. And you could do all of this sort of thing as well. Through R and Python as well. But more commonly, people in sort of the sorts of things that we do, people will more commonly do just embarrassingly parallel calculations of the sort that you might do on a single computer, but when you want to use more cores and distribute your independent computations across more cores. And so oftentimes those sorts of operations on the back end, sort of potentially hidden from you, might be using MPI, but you might not even know. It might not even realize that it's using MPI on the back end.
So MPI is for shared memory or distributed memory, or
you can run it on shared memory, but there's not really any reason to. So it's really for running across multiple nodes or multiple machines. Yeah, and you could even run it across independent. You could run it across Arwin and Baron and some of the other SCF servers without even doing it through scheduling software or anything like that. There's nothing to stop you as long as you sort of tell MPI what are the machines that I want to use. So you could, if you had 4 machines running in your house and they were networked together, you could use MPI to like set up your own little cluster. You can do actually distributed linear algebra using something called Scalapack, and there's an R package that allows you to do that. I won't talk more about that, but just to mention that exists. And then, like I said, you can use MPI explicitly. Okay, and then of course there are GPUs, which are basically you've got a GPU unit on a given computer, and it has thousands and thousands of very slow cores, but because there are thousands of them, you can often get nice speedups from using GPUs. Okay, so maybe we can. So I thought next I'd talk a little bit about some of the sort of strategies for how you manage splitting up your parallelization. And it might be helpful to get a sense of like what are the different things that you guys are parallelizing or thinking of parallelizing. So like what sorts of things do you end up parallelizing?
So for me, it's mostly like I might be doing a bunch of simulations.
Okay.
Or so sometimes, like for example, I'm calculating like I've got some function that might be calculating some kind of similarity matrix or something like that, and that's not so parallelizable. I'm trying to think of an example when I recently did. I don't know, mainly simulation type stuff. It's pretty simple.
So simulation studies where you have many replicates.
Yeah.
Okay.
Yeah,
And
that's
yeah,
pretty much.
I mean that's fairly common amongst what we do. And how long does each replicate take in general?
It varies.
Okay.
Depending on what it is.
Yeah. Okay. What about you? And what's your name, by the way?
my name is Hugh.
Hugh.
And I'm kind of the same as Rita. I'm running some simulations.
Okay.
And you need to run it several times to estimate the standard error and like the mean of the performance of the algorithm. So.
Okay. And how many replicates are you often running?
So there might be like several conditions, like several parameters. So I feel like sometimes I need to run for maybe 4 or 5 hours for a whole set of experiment.
But are the things that you're thinking of parallelizing across, are they like 4 different parameter settings, or are they many replicates in a simulation study?
I think it's like both. So
Okay.
Yeah, you need to consider different parameter setting, and each have you need to run several times to estimate the outcome. So.
Okay. And what about you? What's your name?
Henry? Training convolutional neural networks.
Okay. So are you using GPUs for that, or are you doing
I
it
haven't
on?
actually started doing it.
Okay. Yeah. So so you may already know this, but a lot of the machine learning software is set up to allow you to use GPUs on the back end.
Right.
Caffe, Theano, TensorFlow, Torch, some of the other things.
Right.
I keep meaning to ask some of the grad students who are using GPUs if they have any benchmarks of how fast it is on the GPU compared to the CPU, because it's been I have this feeling that GPUs are not quite as fast as people think they are, so I'm sort of curious how much speed up they're getting, but I keep forgetting to ask.
Maybe Jamie thinks that he gets a decent amount, but I don't know.
Okay, yeah. Yeah, he'd be one of the obvious people to ask.
If you give a big enough cluster, it's essentially the same thing, right?
Yeah, it's sort of right. It sort of depends on how many CPU cores you can collect versus how many GPU cores you have available to you. And what about you, Soren?
The same as
Same.
Rebecca. I also have I have a lot of parameter settings, and then in the end I need to calculate a lot of benchmarks. Actually, it's even the case that I often update things, and I just want to rerun a few things, and then I'm sometimes trying to optimize it to basically say like keeps the data frame and everything we have in place, and just try to change those columns. But it's actually I don't know. I've thought about that. For example, currently I'm blocking our cluster with having like a lot of jobs running, where I request 32 cores, but each core is basically running their own job, and it's no reason for me to allocate all 32 cores. It would be enough to basically run 32 individual things, because I also don't have shared data or anything.
Right.
It's just more convenient for me, and I was wondering whether it wouldn't be cooler to basically have the ability to somehow, or whether it would be nicer for other users to submit individual jobs, because I could easily spread my jobs into like roughly 100,000 individual jobs, and each of them is basically creating their own data, running the simulation, and then it's done.
Right.
And this would be nicer, but then I kind of have like this long list on.
Yeah, I mean, I think in general our scheduler will work a bit better if people had smaller jobs rather than 32 core jobs, just because that means that if there are, say, 3 people running using 1 core, and then somebody tries to submit a 32 core job, that 32 core job has to wait because there are not 32 free cores. There are only 29 free cores out of the 32. So in that sense, it can work better if you've got smaller jobs. Our cluster is not so busy so much of the time that I'm all that concerned about it. But it could be something to keep in mind, and we could talk about if the cluster gets busier about that. But
well, I'm more thinking of the nice thing is on the Lawrence and it's a high performance cluster. There you can apparently have several machines, each of which with several cores. And I was thinking, wouldn't it be nice if I understood how to access 10 machines, and they are doing all my stuff, and then I'm done, and it would be only one job for me, and that currently I'm submitting then 10 different jobs, each of them requesting the entire machine. And
so some of this might be useful, or I'm happy to talk to you separately about that. The thing about the clusters that are not the SCF clusters, usually they give the entire node. And so unlike on SCF, where some people might have 1 core and another person might have 4 cores on the same node on something like that machine, it's probably that you're getting the entire node, and so you want to make sure you're using all the cores on the node as opposed to wasting them.
Yeah.
So a few sort of high-level things that are sort of how I think about this is, first of all, if you can avoid having to use multiple machines and just use one machine that has a lot of cores, it's often the easiest thing to do. And oftentimes doing the communication ends up slowing things down of having to communicate across nodes. So if you can just get your job such that it fits on a single node, and maybe you have multiple jobs and you run one job on one node and another job on another node, that's often the simplest thing to do, but not always. You can't always do that.
With the implementation, is it like, I feel like I don't usually tell it what it should do. I just, at least using the old stuff, just specify how many cores I need, and like if I'm just like submitting it with QSub or whatever.
Right.
Like, which one of these does it do?
So if you're just submitting with QSub without any extra more complicated flags or without any more complicated coding on your part, then you're just using one machine, one node. So So then there are times where people want to use, they need to use 100 cores or 500 cores in order to get things to run quickly enough, or you may need to have your job split up across machines because you want to use more memory than is available on one machine. And so those are cases where you might need to use multiple nodes. So then another thing, and this sort of comes up in what Hugh was saying, is that sometimes you'll have multiple dimensions that you can parallelize over. So in this case, you might have different parameter settings, and then you might be running a large number of replicates for your study. And so then the question is, well, should I parallelize over this dimension or both of them? Usually you don't want to be like writing nested for eaches or nested parallel applies or other sort of nested parallelization. So the first option is basically just to sort of parallelize whatever the outer loop is. In some cases that might only allow you to parallelize across like 4 different tasks, like if you only have 4 parameter settings, and then you could only use 4 cores in that case, so that's not very helpful. So you may want to make sure that you're parallelizing across whatever dimension has many tasks. And I'll get back to that question of how many is too many or too few tasks in a second. But often you want to just parallelize over one of the dimensions that you can parallelize over. And if you do want to sort of if you do have a situation where like maybe you have 100 replicates and then you've got 4 parameter settings, so you've got 400 things that you need to do, and maybe you want to parallelize over all 400. The easiest thing to do is what I'm calling here just flattening the indexing. So just do your parallelization over 1 to 400, and then write your code so that you know that number 3 is parameter setting 1 and it's the 3rd replicate and that sort of thing. And that's usually sort of the most straightforward thing to do, and not try and get into complicated things of like, well, can I parallelize it at multiple levels of my for loop and things like that. Okay, so then the complication that arises is you sort of the rule of thumb is you want to generally have at least a modest number of individual computations relative to the number of processes that you have running. So you don't generally only want to have one computation for each process, because what can happen then is, if let's say I've got 10 cores and therefore I'm running 10 processes and I have 10 things to do, if any of one of those 10 things takes a lot longer than the other ones, then that's going to be the bottleneck, and so you're going to be using up. You're basically going to be waiting until that slowest one finishes. So ideally, if you have 10 available cores, you'd want to split up your computation into something more like 40, 50, 200, 300 independent computational units. And then you can basically have those 10 processes running, and you can start the first 10 tasks going, and then when one of those finishes, you start the 11th, when the next one finishes, you start the 12th, and you just churn your way through the 40 or 50 or 200 that you've got. And if you've got enough of these, let's say you have 200 and you have 10 cores, if you have enough of them, then you get a sort of law of large numbers kicking in. And on average, even just by random chance, you should get that all 10 of the cores are basically finishing roughly around the same amount of time, unless you get unlucky and one of your tasks takes a lot longer than the other ones. So the idea is to try and, if you can, and you can't always do this, but try and split things up into enough things that you've got multiple computational things that need to get done relative to the number of processes, relative number of cores that you have running. On the other hand, you can take it too far, and you don't want to split things up into like 100,000 things that each takes a second, because there is overhead involved in basically starting in basically getting the task running and then collecting the result back. And so if you're doing 100,000 things, each of which takes a second, most of your time is going to be spent basically starting and stopping things and collecting the results back. So you want to sort of be in this sweet spot between the two of those options. And so like in the case with the multi-parameter, the different parameter settings, if you've only got 4 parameter settings and you have more than 4 cores, then you want to try and find another way to do the parallelization, because otherwise you can't make use of all of the cores that you have. And so going to parallelize over the replicates is a natural thing to do there. Any questions along those lines? So then the other thing that comes up is in terms of this idea of making sure that you're using all of your cores for basically the full amount of time that your computation takes to run, is there's something called in R is called PreScheduling, and in Python there's this, it's sometimes called a load balanced view. And the idea is basically if you have you have like 100 different things that you want to run, and let's suppose that the circles indicate how long they're going to take, so they have some differential amount of time to complete, right? And now suppose that you've got 4 cores on which you're running processes. Did I say this last week about dividing these up and dispatching them? I've given a bunch of talks recently, I'm sort of forgetting. So one way that you could do this is in advance, you could take the 100, divide them up into 25 different things, and then, for the first 25, send them all to the first process, the next 25, send them all to the second, the third 25, and the fourth 25, and basically allocate them in advance. And that is efficient in the sense that you only have 4 units of communication because you basically send the 25 at once, so that's efficient. But you could also get unlucky, and suppose this 4th job is just takes a very, very long amount of time. Then that could mean that if that 4th task is running on this process, this one could take a lot longer to complete than these other 3. So if that were the case, then what you'd probably want to do is this is called prescheduling if you sort of chunk it up in advance. And then a more load balanced way to do it would be to basically start the first 4 of these on the 4 processes. When one of them finishes, send the 5th one, and so on and so forth. And then even if this 4th one takes forever over here, these other 3 can be churning through all of the shorter ones while the 4th one is going along. And so there are some arguments to various R functions that allow you to determine whether you do this prescheduling or not, and the same thing in this Python, in the case of IPython, which I'll show you in a minute. Okay, so questions, comments? Okay, so the sorts of things that that tend to come up when you're doing things in parallel that sometimes cause problems is you need to make sure that the worker processes are all starting up correctly and the master is communicating with them. That's often more of a hassle if you're working across multiple machines than if you're just working on one machine, but it's not uncommon for things to go awry and you're like, why is nothing happening? It's because somehow the communication isn't set up properly. The other thing that can happen is, especially if you're working across multiple nodes, you often need to make sure that all of the worker processes have a copy of the data that you need to operate on, and so sometimes that means you need to explicitly basically send the data to all of the workers, which is often called broadcasting. And then sometimes you'll also need to explicitly make sure that all of the worker processes are loading the packages, the Python or the R packages you need to use. And it really varies depending on how you start up and run your parallel code as to whether or not you need to explicitly send the data and whether or not you explicitly need to load the package. But oftentimes if you do need to do that and you haven't done it, you'll see an error message that says, I can't find X, or I can't find package numpy because you haven't loaded it on the workers. Sometimes it gets a little bit complicated that sometimes when you do a parallel, like a parallel apply, in some cases, like particularly in the Python example, it doesn't allow you to send more than one to parallel. You can parallelize across the first argument, which would be like the index of the parallelization of the different tasks, but then it doesn't allow you to send additional arguments. So sometimes you need to sort of work around that and like send all of the additional arguments as global variables to the workers and then basically load them in from the workers. And I'll show you an example of this. But that's something to keep in mind is sometimes you need to monkey around to make sure that you can handle the additional arguments. Another thing is making sure that you have distinct random numbers for your different tasks if you're doing things in parallel. Since I'm talking about that now, I'll just basically give you the high-level overview because I probably won't have a chance to say enough time to say more in detail. But basically, when you generate random numbers or pseudo-random numbers on a computer, you're basically generating from a big periodic sequence, and what's called the seed tells you where in the sequence you're starting your random numbers from. So if you say set.seed, if you say set.seed of 0, maybe you'll end up, maybe this is the location where the 0 seed starts, and then you'll start generating random numbers. And so this will be the first one you generate, the second one, the third one, the fourth one. If you set the seed to be 0 again, you'll just start generating the same random numbers. And eventually, this period on modern random number generators is just immense. Like you could be generating random numbers for the rest of the solar system's existence, and you would never get back around. But what can happen? So what you could do potentially to make sure that you get, you wouldn't want, of course, to have each of your parallel processes use the same seed because then you're going to get the same random numbers. If you're doing a bootstrap sample, you're going to get the same bootstrap data set on every one of your processes, which would obviously be silly. Or the same thing with simulation studies. So one thing you could do is just use a different seed for each of the different tasks that you need to do, each of the different simulation replicates. And that will probably be okay, but it's not really guaranteed. So maybe you set the seed of 0 for the first process, and then 1 for another process, and then you set it to be 2 and 3. It might be the case that these seeds put you in very separated locations on this circle of random numbers that you could generate, but there's not really any guarantee of where this is, so it is possible that you could end up having 1 be like right next to 0. And in that case, you could end up having, you generate some random numbers from starting at 0, and you generate from starting at 1, and now your bootstrap data set or your replicates in your simulation study are correlated because your random numbers are some of them, you share some of the same random numbers. So setting the seed as something to be a unique seed for each one, you probably won't overlap, but there's no guarantee, so it's not very good practice. So later on in here and in the tutorials that I linked to, I have a whole bunch of gory details of how you can use packages in R to make sure that you are basically, what it basically does is it makes sure that it says, okay, on the first process I'm going to use these ones, second process I'm going to use these, third I'm going to use these, fourth I'm going to use these, and so on and so forth. And it's just sort of a matter of knowing what the syntax is. I don't think Python allows you to do that, so in Python I think you just have to set the seeds to be distinct. That was what I learned 2 years ago. I don't know if that's still true, but I haven't looked it up recently. And then the other thing that comes up is just debugging parallel code can sometimes be a hassle because often, it's often a little bit hard to tell whether the workers have the data they need, and sometimes the error messages don't come back and you don't see them, or they get buffered, or they get printed out somewhere you're not expecting. So it can sometimes be somewhat hard to debug these things. And so it is usually good practice to make sure that your code runs properly just on one core in parallel before you start trying to send it off and do it in parallel on multiple cores. Okay, so I'll show you an example of, well, how many of you have already used for each or MCL apply in R? Okay, so maybe I'll skip over this for the parallelization on one core, but just briefly, of course, the example that I'm going to use for the various demonstrations is it's a sort of silly toy example, but basically I'm going to create a data set to do regression on where I'm just generating some y's that are nonlinear function of some x covariates. And here there are 50 covariates, but I'm only using like 3 of them to generate the data, so 47 of them are sort of dummy covariates. And then I'm going to fit a random forest using leave one out cross validation. So basically the parallelization is going to be over the 500 different observations. I'm going to sequentially leave out each of the observations, and that's what I'm going to parallelize over. So I have 500 tasks that I need to do where each one of them is holding out an observation. And then I'm just returning so this is using the random forest function in the random forest package in R, and then I'm just returning the prediction for that single held out observation. So sort of realistic, but fairly simple. So for each would just basically you could put in some print statements, and what you'd see when you ran this, this is obviously a parallel for loop. It's just going to run through, and it's going to sequentially loop through I, where I goes from 1 up through the number of held out observations that I'm working on. And if you did this, what you'd see is it would say starting the first one, second one, third one, fourth one, and then it would pause while it was completing. So you could see that this was actually not doing this pre-scheduling, that it's actually doing it in a more dynamic way. Okay, but most of you have seen that. So then there are examples in here of similarly you can do a par-sapply. And if you're going to do par-sapply, you basically need to call this make cluster command and tell it how many cores you want to use. And so that'll sort of establish things so that par-sapply then can dispatch the work to the multiple processes that get started up. And then there is also MCL apply. So the usual curse of R is that there are 17 different ways to do the same thing. But you can also do it with MCL apply, and there all you need to do is just say how many cores that you want to use. So for all of these, if you ran top, what you would see is individual processes running, as many as workers that you're using here. Okay, questions here?
You had a little comment.
Huh?
Make one of the things that was like when the cats aren't appearing, the things you're trying to print don't appear.
Oh, where did I say that?
Right there. That's always something that has frustrated me.
Oh yeah, this was actually even.
That might not have been.
Yeah, this is actually not even an R Markdown file anymore. I think this was left in there for when it was an R Markdown file, but things were not printing out. Yeah, I'm not sure I have a solution to that. I feel like there are so many different contexts in which this can come up that there are probably times in which I figured out how to do it, and then I don't remember. Yeah.
It's somehow not showing up on my laptop, but it's showing up on the cluster.
Huh.
So
Okay.
I put files to cluster, which is nice because that's where I actually run most of my
Right.
parallel stuff, right? But
Yeah, that's weird.
it is annoying when you are debugging stuff because you have no idea where you currently are.
Yeah, because I always print something which is literally using it's just printing I,
Yeah. Right.
so I can see where I am.
Yeah. So if you're at a point where that's frustrating, I'm happy to look at it, but it'd be the sort of thing where I'd just give me like an example of it happening, and then I can try it out on our Linux machines and on my laptop and see if I can give you a hand with that.
So I'm curious about how when you run multiple processes using this, like how it managed to access the memory if there are two processes, they are trying to modify the same
Right.
same thing,
Yes.
variable. Like is that variable like has been like duplicated or like how?
Yeah, so this is wordy, and if you wanted to, you could read it separately. But what basically is happening, and it's slightly different depending on which way you're doing the parallelization, and whether it's doing something called forking versus making new processes. But in some cases, and I guess if you do for each on a single machine, what it's going to do is the current R process does something called forking, and what that basically means is identical copies of that R process are made, and then they can communicate back to the original process. And so when those identical copies are made, new copies of all of the data objects are made. And so those are copies, and you could modify those, and it won't affect the copy on the original. Yeah.
So is there a way in R to don't use this like fork?
Well, the other way that these parallel processes get started up is that your one R process could like go to the operating system and say, "Hey, operating system, I want to start up a new R process," and that's slightly distinct from this idea of forking. And when that happens, the new R process will start up, but it won't have any of the data that the master process had, and then you would need to make an explicitly broadcast the data from the original process to the worker processes.
Oh, so
But it would still make a copy.
yeah, but the question I have in mind is sometimes I need to run some like optimization algorithm where I would like for example like block coordinate design, and I would like different cores to actually modify the same matrices or the same vector,
Right.
and I would like so they might update in different blocks, but they are actually updating the same vector, something like that.
Yeah, so you could, if you were writing code in C or C++ with OpenMP, you can definitely do that. I don't know if there's a way to do that in R or in Python.
I see.
Yeah.
So if I use MPI to do that, so it's like shared memory.
Oh no, so there's MPI, which is for distributed memory, but what I was saying is that you could use OpenMP.
Oh.
And OpenMP is for writing threaded code.
Oh.
And when you write OpenMP code, you could basically assign into the same vector from different threads. So that would be one way to do it. Okay, so depending on exactly whether the workers got started up by forking or whether they get started up by starting independent jobs, that will sort of determine whether or not you need to copy data to the workers and whether or not you need to load packages explicitly on the workers. In some case, that's sort of the rough outline of what happens. And so basically, you just sort of need to keep in mind that might be necessary in some cases. And I do have some documentation here of exactly when it's necessary, but it's just sort of the tedious details. Okay, so then I wrote up code to do the same thing in Python. So if we're going to do this in Python, basically what you can do if you're running on a single computer is, I'll do this on R1, you can basically start up a cluster, and this was going to start a cluster with 4 different workers. And so what we should see if we ran top when we're doing this is we should see 4 different Python or IPython processes running. And I just put sleep here because I need to make sure they all start up before I actually run IPython. And then basically this is doing the same generation of that same data set and then running a random forest on it, but using a Python package to run the random forest. And actually I'll just go over here. Okay, so I now have the workers started, so now I can run IPython. And I can run this. And so I loaded in this IPython parallel package, or sort of a sub-package from it. And then I run this client function, and then basically this IDs object that's part of this client object basically tells me that I have 4 workers available to me. And then the sorts of things that I can do are I can say, okay, I want what Python calls a direct view is the pre-scheduling that I had indicated over here, where it decides in advance it's going to do 25 on one and another 25 on another and things like that. So I could, for example, I can basically make a direct view into these worker engines, and then I can run a function on each one of the worker engines. So this is just running an anonymous function that's just going to print back hello world, just to sort of make sure that each of the worker engines is running appropriately and I can communicate with them. Blocking usually has to do with whether or not you have to wait explicitly until all of the results come back, or whether you could keep doing things in Python while things execute asynchronously on the workers. I don't quite remember why I put that in here for this particular example. But what we'll see here is it should return back 4 different hello worlds, 1 from each of the workers. But in terms of running through and doing the parallel leave one out cross validation, for that maybe I'm not so sure whether or not each of the held out fitting is going to take the same amount of time, and so I might want to do it in a load balanced way, where I'm sort of dynamically allocating the different tasks that I want to do. So then what I'm doing here is I'm going to set up this object called a load balanced view that will allow me to then to run things in parallel in this dynamic way. And here's an example of where I need to import Python packages on the workers explicitly. So I'm going to run this command in parallel using the direct view. And I'm going to execute that in parallel on each of the workers. And then I'm going to need to transfer the data all to each of the workers. So I'm going to create a dictionary, a Python dictionary that contains the function I'm going to use and the input data and the input covariates. And then I'm going to use this push function to basically take that dictionary and push it onto each of the workers. So that's how I'm distributing the data to the workers. And then this is an example where it's a little bit complicated, that in order to run, I want to run this leave one out fit function in parallel. But in order to run that, I can only have a single argument that is passed into that function. And basically when I do the parallel, basically a parallel apply, or in Python it's called a map, a parallel map. When I do that, I'm basically going to execute the same function on the numbers 1, 2, 3 up through 500 for the 500 different leave one out observations. But I also need to pass in the x and the y into my leave one out fitting function. So I need to pass the data in. So the way that I'm doing that here is, if I'm going to do this map function, I can only pass in the function I want to run, and then the indices 1 up through 500 or 30. In this case, I'm 50. I'm just doing a subset. So I can't pass in any additional arguments to my function. So then what I've done is I've created this wrapper function, and the wrapper function is just a function of a single argument, which is what's required for doing the mapping. But then because I pushed the x and the y onto each of the workers, I'm going to call LO fit with I, but then with the y and x that are already on the workers. So that sort of idea of pre-staging things and then having a wrapper function is sometimes what you need to do.
This is very interesting, like, because you so for different workers they have different y, but they all have the same name y, right?
No, they actually all have the same data object y and the same covariate matrix x. And then in my leave one out fit function, which is up here, depending on the index, which is going to be 1, 2, 3 up through 500, depending on what I'm doing, then I am, what am I doing here? I am, oh, this is, maybe there's a better way to do this in Python, but I'm basically removing the index row from the X matrix, and I'm removing the index value from the Y vector.
Yeah.
So that's doing the holdout for
Yeah,
the
but
training.
because it's like a forked version of the same matrices for each worker. So
Yeah, all the workers have the same matrices and the same vector, but then they're told that to operate on a different I value.
okay, so but here like when you actually call the function, like you use the name Y,
Mhm.
and that seems to be the name for your like master node, right? Like,
Well, it's also the name on the it's also the name of the objects on the workers, because when I push this dictionary, I name the names of the elements in the dictionary are capital X and capital Y. So these are the names of the variables on the workers too.
oh,
Yeah, so that illustrates a few of these ideas of sort of wrapping and pushing stuff to the workers. And so then to run it in parallel, I call this map function, which is basically a version of is basically like an apply in R. If you're sort of familiar with functional programming, what people call a map is basically just applying the same function to different objects or different data points or data structures. And so you could think of it as that an apply in R is just basically a map operation. So this is a parallelized map operation with the wrapper function. And then this will return everything to the master process.
so is there a way to push, for example, X to a specific node?
I think that this parallel functionality in this particular way of doing it in IPython is really more focused on you would just want to distribute the same operation to many different nodes. There might be other functionality in IPython parallel that I haven't looked into that would allow you to do things in a more granular way like that, but I'm not too sure about that. Okay, so then I keep doing that, and then once you're done. Once you're back in your shell, then you want to stop the cluster with this IP cluster stop so that you stop the worker processes. Okay, so then I'll say a little bit about if you want to parallelize across multiple machines in R and Python, and then wrap up. So if you're going to do a for each in R across multiple machines, you need to use a backend that allows the master to communicate with the different workers on the different nodes. So that would either involve using MPI and the do MPI backend, or there's also something called do snow. And the nice thing about the do snow package is you don't have to monkey with MPI, which is sometimes a hassle. And so with do snow, you basically just need to tell R what are the names of the machines that I want to run the workers on, and how many cores are there on each worker, and then you can set things up with that. And you can also do parallel apply statements in R if you set up a cluster of cores across multiple machines. And then that same IPython parallel code that I showed you will work across multiple nodes as long as you start up the IPython cluster in a particular way that I'll show you. So if you're going to run for each with do MPI, you basically need to start up R via MPI run. And so this will basically set things up so that R and MPI are sort of talking to each other, and then R is able to use MPI to basically start the workers on the different nodes. And so if you were doing that on Savio, or if you're doing it on the new SCF cluster, and this were being run in a Slurm batch job, then you don't need to tell MPI what are the machines that you're going to run on, because MPI communicates with Slurm and it knows what are the machines that are allocated to your job. If you were going to do this outside of Slurm, then you actually need to need to give it a file that actually contains the names of the different nodes that you want to run the jobs on. And that .hosts file would generally look something like this. It would basically name the machine and then say how many cores you want to use on that machine. And then you'd have this slots equals syntax. Okay, so then the code in R looks pretty similar. You just need to load in. You need to do this start MPI cluster, and then you need to register that cluster with do MPI, and then you can use for each in the same way that you would have on a single machine. So any questions about that?
So I think right now like the quota for us is like 12 cores, right? So,
No, you can only if you're using the high queue on the old cluster. Yeah.
but low queue, like,
Yeah, the low queue, you're not limited. You could, I think we asked that you not use more than 100 cores at once or something like that, but that you're not. It's not a particularly. It's a fairly large limit.
so basically for this type of parallel over nodes, so it's useful when you use low queue because.
Right. Yeah. So this wouldn't help you very much with high queue. This would only be useful for the most part in the low queue, where you could use more cores than a single node has. Yeah. Okay. So then, if you were going to do snow, you don't need to start R with that MPI run before it. You can just start R in the usual way, and then what you need to do is you need to basically say, here's a vector of the different. It's basically a vector that contains repetitions of the names of the nodes, and the number of repetitions is basically the number of cores you want to use. So this would use 1 core on Baron, 1 on Gandalf, and 2 on R1. And then you would say, I want to make a cluster, and I'm going to use this vector to tell it what machines to use. And then if you don't want to use MPI, you need to pass this additional argument that tells it to make a thing called a socket cluster, which I don't actually understand all the details of, but it's basically avoiding using MPI. And then you can do the same sorts of thing as you're going to register this cluster with this register do snow, and then you can go ahead and use for each. So that's a nice way to get around having to deal with MPI, which is sometimes a hassle. But if MPI is not working on the SCF, you should let me know because we need to fix it. But it does every so often. It's a little bit troublesome. And then if you're doing when you're using for each across multiple machines, you do need to make sure that you load all of your packages on the workers. And so you can either do that by loading it in the function that you're running on all the workers, or with for each there's actually a .packages argument, and you can actually say explicitly that these are the packages I need to load on the workers. On the other hand, you don't need to copy data from the master to the workers, because for each actually realizes that you're trying to use a particular object, and it will then, behind the scenes, it will make the copy for you. So it's actually fairly clever in that way. Okay, and then there's also a way to set up a cluster, to use this make cluster, again giving it the names of the machines. And then if you make that cluster, then you can use that R cluster of workers with a par supply as well. So you could actually do par supply across multiple nodes. As well as within a single node.
And the machines you're giving it is Aaron, Gandalf, and I mean those. This
is just an example of if I happen to want to parallelize across just some of the standalone Linux servers, this is how I could do it. If you were doing this on the cluster, then you would need to sort of programmatically figure out what are the nodes that are
going to be assigned to
what are the nodes that are assigned to my job, and then you need to read that into R. Actually, we actually create that information in a file when the job is started. So if you did want to do this, you could ask me because I can tell you how to do it more easily, but I don't know the details. I don't remember the details off the top of my head. Yeah. So the idea is ideally you wouldn't want to hard code this in. You want to programmatically get it from your environment so that it would work whenever you run your job.
And also, you wouldn't want me to run stuff on Arwen, Gandalf, and Baron, right?
If you're not using up all of the cores on a given machine, it's actually okay. But there's not, unless the clusters are busy, there's not really any reason to do it because these are older machines. They're going to be slower and they don't have that many cores on them. But you can use these machines for this sort of thing if you want to. Yeah. Okay, so then let's see.
And then you would have to first log into Arwen and run your code. Could I then run it just on my computer and it would do everything?
Well, you'd probably need to log into one of the SCF machines in order that the networking would work. I don't know if you could do it from your machine. Yeah. So if you want to use the same IPython parallelization that we saw a few minutes ago, the only thing that the Python code for actually doing the parallelization in Python doesn't change at all. The only thing that changes is that you need to start up the Python cluster of workers differently. So there's a little bit of syntax here. There's this IP controller business, and you need to wait for this controller to start up. And then if you're using Slurm, you basically need to start one of these IP engine processes for every core that you have available. And the nice thing about it is that IPython will realize that it's running within Slurm, and so if you, well, that's not quite the way this works. If you do this via this srun command, then basically what will happen is for every core that you've been allocated, there will be an IP engine that gets run, and so each time IP engine is run, it will start up a worker process on one of the cores in your collection of nodes with all of their cores. So it'll sort of, as long as you have this srun here first, it sort of all happen magically behind the scenes. And then once all of these have started up, so maybe you have requested 3 nodes and they have 72 cores between them, this would start up 72 worker engines. And then you could then start up IPython either manually from the command line, or as a batch job you can start IPython, and it will then just do everything in parallel across those 72 processes. And then shutting things down is basically the same as it was before. Okay, so sort of running out of time. I'll just say something very quickly about MPI, since people sounded interested enough to know what it was about. So basically, when you're writing MPI code, as I sort of said before, you basically there's a sort of a limited subset of commands that you would use, and the sort of commands are things like send and receive, and that's this notion of I want to send this chunk of data from this process to this other process, and I want to and you have to pair it with a receive. So then the other process has to say I want to receive a piece of data from the process of that other process that's sending it to me. So if you're doing sort of very nitty-gritty MPI coding, these are the sorts of commands that you would use. But you can also do sort of MapReduce kinds of things. So there's this scatter that will send data out from a master to all of the workers, and gather will pull things back from all the workers, and then reduce will do things like you could do a reduction that's like a sum, and that will basically sum all of the values that are on all of the different nodes and collect the sum back to the master. So there's a fair amount of flexibility in what you can do, but it does require a lot of sort of nitty-gritty coding. And so the sorts of this is just sort of a hello world example. Basically, the way it works is that when you run MPI run, and tell it, oh, I want to run MPI run and do that on, say, 16 processes. What MPI does is it basically runs the same code on every one of the processes. So it's running identical code, which makes it seem like, well, how do I control if this worker does something different than that worker? And the basic way you do it is that you'll have these different MPI commands, and what this command does is it will basically say, how many total workers do I have? And it's going to put that in a variable called nprox. And then this rank command will basically say, what's the ID of this particular process? And it will put that in my rank. So when this gets run on the first process, my rank will be run 1. When it gets run on the second process, my rank will be 2, and so on and so forth. So then if you were writing real code here, you could say, if my rank equals 2, do this. Or you could say, if my rank is 0, so if I'm the master process, then write a for loop, and I would send this data to 1, and this data to 2, and this data to 3. So you can basically use these things programmatically so that it actually makes sense that you have the same code running on all of the processes, but they do different things because you've got these if statements where you're controlling how each one of them behaves. And so the way you do these things is you write code like this. You call a version of the compiler that is sort of MPI aware to produce an executable, and then to run the executable you call MPI run, and then the name of the executable. And if you're not running in Slurm, then you may need to explicitly say what machines and how many processes do I want to run this parallel code on. And then I'll just show you one quick example of a slightly more interesting piece of MPI code. So I'm actually sort of forgetting what this does. At some point I knew what this did. So you can sort of see the same thing happening here. This is going to figure out what the rank is and put that in this myID, and then it's going to figure out the total number of workers. And then this is sort of the style of what MPI code looks like. It says, if myID is master, and master is a variable up here that's 0, then this is just code that will execute on the master. And so it's going to do some printing, but it's going to do some preparatory stuff, and then it's going to broadcast out some data to all the workers. And then there's another chunk of code that says if my ID is master, it's going to do some sort of calculation, and then it's going to send a particular chunk of data to a particular target node. And you'll notice the target is P, and I'm looping over P. So this is like iterating through and sending some data to each of the different workers, depending on what's appropriate. And then what you would see is in the else, so this is an else where the if was if it was the master. So this is going to run on each of the workers. And then each of the workers is going to do a receive to pull in the data that the master sent out. Each of the workers is then going to do some sort of calculation, whatever calculation is appropriate for the worker. And then at the end of the day, in this particular calculation, there's a reduction step where it's doing a sum across all of the subtotals that are on each of the workers to get back whatever it is that this computation is doing that the master can then process, because it gets stored in total here. So that's sort of, obviously very, very quick, but that's sort of the style of how you'd write how you end up writing code in MPI. And you can write code of this style if you wanted to from within R or Python, but the syntax would change, the names of the functions changes a little bit. Okay.